Okay, welcome back. This is Module 8, Introduction to Probability. This is page 4, and full disclosure, this is my 4th recording of page 4. I have deleted one. Anyway, long story. So please, 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 if I leave anything out, because I'm convinced I said it, but it was one of the previous recordings, please contact me and let me know where your questions are. So, up above, page 3, we talked about the theoretical method or the classical probability method, using what we know about total possible outcomes and the number of ways that some event could happen. We are now going to talk about relative frequency probabilities, which is also called the empirical method, used to be called experimental probability. So we are going to run multiple trials of an experiment, and the probability of an event happening are going to be based on what we see happening in those multiple trials. First thing I want to do is back up. We talked about what happens when we roll a die. Didn't get specific enough to take a look at the probability of each thing happening. When I say each thing, I mean the sum of our two die. So here in example 3, we're going to roll a pair of dice 20 times to calculate the probability. Now, full disclosure, if we were in class, you each would have rolled the dice 20 times, and then we would have tallied them together and come up with the 400 or 500 or 600 total rolls from the class. Because we can't do that, I deviated a little, did not really roll these. I used a simulator online, and we're going to talk about simulation probability in the next one. But just know that I'm kind of stretching that experiment right now to meet our needs. Okay? So we are going to look up above at our table, and we're going to look at the theoretical probability of rolling these sums. And I'm going to go through a couple of examples. I'm not going to do every single one. Bill Itty. So rolling a 2. Let us change this up a little. And not use that because that's not going to be helpful. There is one way I can roll a 2. A 1 and a 1, if I add those together, I get a sum of 2. So I know that the probability of rolling a 2 is 1 out of my 36 different possibilities here. Let me see if I can color code with a bud, make it look a little easier to find. If I want to roll a 3, the only way I can roll a 3 is that 1 and 2, or 2 plus 1. So I know down here the probability of rolling a 3. There are 2 ways I can do that out of my 36. I'm going to do one more, and then I'm going to go ahead and fill in the table, and you are welcome to come back here and take a look at these if you would like. If I am rolling a 4, it's 1 plus 3, 2 plus 2, or 3 plus 1. So I come down here to the theoretical probability of rolling a 4, and that is 3 out of 36. 5 is 4 out of 36. 6 is 5 out of 36. My 7 is 6 out of 36. We know our 8, back to 5 out of 36. 4 out of 36 for a 9. I am not going to convert these to decimals because I don't want to make this video really long, but you can double check those and see how our probabilities hold up here. So in my first 20 rolls, I rolled a 4 5 times. So 5 out of 20, that gives me a probability of 25%. I rolled a 5 1 time. I rolled a 6 3 times. 7 happened 4 times. 8 happened 3 times. 9 happened once. 10 happened 3 times. I'm going to add all those together. Make sure that I get 1. Notice here in my 20 rolls, I did not roll a sum of 2 or 3 or 11 or 12 once. And that kind of makes sense with our probabilities, right? Those happen less frequently. So the goal was to hit 1,000 rolls, but the online dice roller would not tally those for me. So I petered out at about 137 here, but you can take a look at the shape and notice that it follows the trend for our theoretical probabilities a little bit better. 7 happens more than anything else, then 8, then 9, and 10-ish, a little bouncing back and forth. 6, not quite as many as we expected. But again, more trials, closer to what we expected to happen. So let's take a look at our probabilities. That should not be 17, that should be just 7. Obviously the eraser is set to erase too much. So I get 0, 5, 1, 1. 12 over 137. Actually, what I'm going to do is go ahead and pause and fill in the rest of this table so that you can pause and copy down what you want. Just kidding, it won't let me write anything on here when I hit pause. So we're at 27 over 137, 0.1971, 18 over 137, 0.1314, and where are we, 14, .0292, just like with 2. Okay. So this takes us to what is called the law of large numbers. And this is important to remember. And the law of large numbers says the observed values or averages from a sample will get closer to the population averages as the samples get larger. Okay, now I am going to change this up just a little. Our observed values and averages. Those are, and let's change color. Those are our relative frequency probabilities. Those will get closer to our theoretical probabilities. As our samples get larger or as our number of experiments increases.